All right, so we are, leave a page in your notes. If we have time, we're going to go back and do one more Rolle's theorem. But let's at least learn the new stuff first, and then the other might be a good review. So leave a page. If we don't fill it, that's okay. But leave a page that we might go back to Rolle's theorem. Okay. But let's go on to still section 3.2. Part 2, last part, we want to talk about the mean value theorem. And you'll also want your sheet out, because that's the third thing. Remember, and you'll have this for the test. I'm okay with that. You're still going to have to check stuff off. You're still going to have to understand what it's saying and how to use it. All right, so let's look at Rolle's theorem. The reason this is together is because they're related. Okay, so let's just look at Rolle's real quick. Rolle's theorem said what? If they're the same height, if A and B are the same height, then there has to be at least one C value that is a max or min. Okay, or has a derivative of 0. But this is also kind of cool. If you look at it a little bit differently, if we draw a line through the endpoints, the slope is 0. What about this tangent line? We said this C would be a maximum or a minimum, or we already said would have a slope of 0. So the mean value theorem says, hey, what happens if these aren't the same height? So the mean value theorem, and mean, we're going to write it in a minute, mean meaning average. That's why it's called the mean value theorem. So we'll talk about where that average or mean comes in just a minute. Mean value theorem. All right, so the mean value theorem says, what happens if A is here, but B is up here? We can either mark it down here like at the x-axis, or you can mark it up there, it doesn't matter. So if we connect these two, and we talk about the slope of this line, whatever that slope is, there is a point on the graph, the mean value theorem that says there is a point on the graph that has the same slope. It won't be 0 because now this guy isn't 0. But do you see how this slope matches a point on the graph? It's just the one that we really care about, those max and mins. But this will also come into play. So there is a point somewhere on here that has the same slope. Has the same, so what should these two lines be? They should be parallel. And this is now our C. Is that C a max or min? I kept saying we're talking about max or min, but today it is not a max or min. Okay, this is just saying this, let's call this M1, because whatever that is, this has the exact same slope. Okay? These two lines have the same slope. C is that point that has the same slope as the endpoints. C is the one point that has the same slope as the line that connects endpoints. Move out of the way here. C is the one point that has the same slope as the line that connects the endpoints. The line that the line that connects the endpoints, its slope is called the average. This one is the instantaneous. All right, so let's look at what this guy's saying. We'll still tie it to this picture, so don't let it go away completely. I'll put it up for 1 second, maybe. I'm trying to learn how to get this to go here. Oh, not that one. So I'm going to do a new share and make sure that you have this sheet. I think they can see. Make sure that you have this sheet if you're out there in TV land. You guys want this sheet? We're going to be looking at the mean value here. Okay. So in your notes, you can either put, for now, let's write mean value theorem. You can either put C note sheet, or if you want to kind of leave a little space and write it in there. So now let's write something for, let's write mean value theorem. And then we might actually write something anyways in our notes, but basically what we're going to be following is steps 1, 2, and then talk about what it means. Okay. Okay. All right. So the mean, and we can go through it, it's even shorter. Notice what are the two things? It still has to meet requirements. It has to be continuous and differentiable. Do you see what we're looking at down here? So just make sure that you still have this sheet out. It's still f of x, still has to be continuous. We'll just do it really short. And f of x has to always, on the closed interval. And it has to be differentiable on the open interval. We still don't care about the endpoints when we're talking about the derivative. Okay, if that's the case, then there's a c for the derivative that is equal to f of b minus f of a all over b minus a. Okay, do we see that? It's right here on the sheet. We're just copying the sheet. What's going on here? Do we see in here, this is, what does f of b stand for? Like y, right? So this is like y2 minus y1 over x2 minus x1. So that is literally finding slope with 2 points. That's finding the slope of the line that connects the endpoints. This is slope. Okay, again, I think the same thing that I wrote here. This is the side, this is the slope of line through endpoints. And this one is the average or mean, average rate of change. Does that make sense? The average, we're just doing the endpoints. So we consider that the average, or that's why we call it the mean value theorem. And then what's this one? That's the derivative at 1 point. So that is slope at 1 point. This is slope at 1 point. Slope at 1 point, because we're talking about the derivative. So the derivative means we only have to have 1 point. Slope at 1 point, or the instantaneous rate. Instantaneous rate. All right. I think that one. Do we see, maybe I should have done it. This side is talking about, that probably doesn't show very well, that's talking about this 1 point here. Slightly better there. That's talking about this point, and this is talking about literally the slope of the 2 endpoints. Okay. But remember, it's kind of cool that as long as it's continuous and differentiable, there will be at least one point that has the same slope as the endpoints. Okay, that, should we say that? That's kind of the mean value theorem in a nutshell. Okay, there's that, as long as the graph is continuous and differentiable, there will be at least one point, if not more, that has the same slope as the slope of the line that goes through the endpoints. Okay, so let's do that there, we did all that. Oh, I know one other thing we could write. This is, last thing, this side here is the secant line. Secant line. And that one over there, what do we keep calling this one? This one is the, what's the try? Find the slope of the line of the tangent. Yeah, so this is the secant line, and this is the tangent, or a tangent. Secant line, and then that's the combination. That specific secant line goes with that tangent. All right, good. We did all that. Okay, let's do some examples. If I put a marker here, it's showing up. Doable. Okay. All right. Let me just make sure. Am I sharing the camera? Yeah, okay. Just because when I flipped around, I get nervous. Okay, so let's clear the board. Let's put up some directions. And then this formula, though, is the one that we're going to use. All right, so the directions say, verify that the function satisfies the mean value theorem. Mean value theorem. Then find C. That, and if you just want to put that, that's okay, but that satisfies the conclusion of the theorem. So we have to verify that it meets, and remember, the mean value theorem only has two things, continuous and differentiable. Okay? Then if those things occur, then we're going to find C that satisfies the conclusion of the theorem, which is what I just erased, that the slope of the endpoints, the line that goes through that, we can find that C value that has the same slope. So that's what the conclusion is saying. All right, so let's, I have, okay, let's try this one. F of x, there we go. F of x equals 3x squared minus 2x plus 5, and we're going on the interval from 1 to 3. All right, so you look on your sheet. Somehow on the test, you're going to have to say 1. Is f of x continuous? It only has to be continuous from 1 to 3, but polynomials are always continuous. If you have to make some statement, you can say it is continuous on 1 to 3. You can say polynomials are always continuous. Either one. Does it make sense that if it's always continuous, it definitely covers from 1 to 3. Okay, but remember, we really only care about from 1 to 3. Okay, now to see if it's always differentiable, I mean, I would be okay if you say, hey, polynomials are always differentiable. That would be okay. Sometimes what I like to do is look at the derivative. we're going to need it anyway. So what is the derivative? We're pretty good at that, right? Roll it down, subtract 1. So this is going to be 6x. Negative 2x goes to negative 2, and the 5 goes away. Is there ever a time where a line is not differentiable? No. Okay, so that's always differentiable. Again, we can call it a polynomial. We can write let's write this. Always has a derivative. Okay, but remember, really, where does it only have to have a derivative? Not even including 1 and 3. It really only has to have a derivative between 1 and 3. But we're using the word always, so that definitely includes. But remember, it doesn't even have to be the endpoints. Something like that is okay if we want to go on and then say f of x is differentiable on, we can even write this again, that's okay too. Anything like that, you don't even need both if you know. And again, on the homework, you're just going to kind of verify, but just write at least one of those for the test. Okay, that's it. So now we can go ahead and find C that satisfies the conclusion. So where is this point that satisfies this? F of B, F of B minus F of A all over B minus A. We're looking for C. If we want to be, well, let's hold off and then we'll do it in just a minute. We have, what are these guys? These guys are x's. That's not an xy combination. Those are two x values, right? That's a start and a stop. So the first thing we need is the y values. And so we're going to have to write this again. I just kind of wanted to see what we're referencing. So we need the y values. Y values on the original graph. So the first thing we're going to do is we're going to do f of 1. That's really f of a. We could even, should we write that? We could write this. There's a couple ways we can write it. We can write f of a, which is f of 1. And then we notice we're not doing anything with the derivative. We just got to go find the y value. So it's got to be 3 times 1 squared minus 2 times 1 plus 5. Oh, let's see, that gives us what? 3 minus 2, so 6. And then f of b is f of 3. So now we got to do 3 and come back to my original. 3 squared minus 2 times 3 plus 5. That should be 26. Okay, so now we can write it like that, and we can just go to our formula if we want. This is A and this is B. Or we could also write it like this. We could write it as 1, 6 and 3, 20. And so then we plug it in. The derivative, we could do x or we could do c. So the derivative is 6x minus 2. We can either write it as 6x minus 2 or we could write it as 6c minus 2, either one. They like to remember, they like to call these x's c's. They think there's too many x's. So it's more to identify this specific point. So kind of like to actually name it, then they call it c instead of a general x. With this, I just grab the derivative, which we already found, and then it's equal to y2 minus y1 over x2 minus x1. Or you can just read what you found, or we can do it like this. y2 minus y1 over x2 minus x1. And then we go find the c. 6c minus 2, that gives us what? This is kind of nice. This gives us, are we okay with writing 10? Right, so this would be 20 over 2. Add a 2 to both sides. 6c equals 12. I'm running out of room, but I think we're okay. Divide both sides by 6. And c is 2. C is 2. Okay, what is that telling us? When x is 2, the tangent line, when x is 2, has the same slope as the line that goes through the endpoints. Does that make sense? The point where the x coordinate has 2, its slope, the slope of the tangent line at 2, has the same slope as the line that's going through the endpoints. All right, let's try another. Maybe a little bit harder than the one on your homework, but that's every once in a while. Sometimes if it's too easy, then it's confusing too. But let's see how we do on this. All right, we got 3. F of x equals 4 plus the square root of x minus 1, and the interval is from 1 to 5. Okay, so is this always continuous? This is definitely not always continuous, because if there's a negative, if x is -7, we don't have a graph. So that is definitely not continuous. I mean, not continuous can be a space in the graph, but it can also just mean literally there's no graph there. So we have to think about what causes this to be x minus 1. It has to be greater than or equal to 0. Equals okay. 0 under a radical is okay. And then anything greater than 0 means it is positive. So what does this say? X has to be greater than or equal to 1. As long as x is greater than or equal to 1, we're in good shape. Okay. And what is our interval? 1, including 1, but that's okay. We're saying it's okay to include 1. And then we're saying anything greater than that, this is just stopping at 5. So it is continuous over this interval. As long as x is greater than or equal to 1, we could write it is continuous. We'll just put as, it's again, just in your notes, as long as x is greater than or equal to 1, it is continuous. And that fits, we could even write, and that fits the interval. And that fits. And I'm okay with that. So that's 1. Is it always differentiable between, not even including 1 and 5, but literally between 1 and 5? So for 2, let's go find the derivative and take a look at what's going on there. So the first thing I'm going to do is write the f function, because I'm going to write it as 4 plus x minus 1 to the 1/2. One of the first days we said, you got to be able to work with fraction, or you got to be able to work with negative exponents. You got to be able to work with fraction exponents. Kind of go back and forth. Okay, so let's take a look at the derivative. That's at least nice. Derivative of 4 goes away. the derivative of this guy. Roll it down, subtract 1. But we did it on a quantity. So we had to take it times the derivative of the quantity, but we get lucky because the derivative is 1. So I don't want you to forget that, but they are kind of nice. They make them pretty basic. The derivative, though, we'll write it, though, is 1. You have to always do the derivative of the quantity. Okay, so that means that the derivative is, there's really nothing on top. There's just this 1. The 2 is on the bottom, and because this is negative, we're pushing it back down to the bottom, x minus 1. Are you okay with, and we don't have to worry about the 1, but are you okay how this and this are really the same thing? Got to be able to slide them around now. Negative exponents, push it down, make it positive, change it back. If you like visually, I like to see the 1/2 back as a radical. Okay, so now here, we want this to always be positive, right? A square root, no matter where it is, has to be positive. But if this equals 0, is that okay? That is not okay, right? Because now we got a 0 on the bottom. So this time, x minus 1 has to strictly be greater than 0. It cannot equal 0. Because now, because of the derivative, we created a fraction. Here we had a fraction, so 0 was fine. So we kind of have two things going on here. We got to think about the fraction, the bottom being 0, and we got to think of the square root being positive. Okay, so that means what? X has to be greater than 1 for the derivative to be okay. For the derivative to be okay, x has to be greater than 1. But what does step 2 say? It has to be differentiable on the open interval. So this is saying not equal to 1, greater than, but that's what this is saying as well. So we get lucky, it's right there on the border, but as long as we understand how to read this, this means doesn't include 1, and actually this doesn't either. So it's a perfect match. Okay? So we can just write, just even, if you just show something like this, I'm okay if you say f of x is differentiable on that open interval 1, 5. You can just say something like that. Kind of like, yep, you checked it, just showing this, you checked it, so we're in good shape. Okay, so now we just remember all that is just the check. It's a little tedious, but we just have to check that it's always continuous on this interval and it's always differentiable. Okay? And sometimes that takes a little bit of work. The polynomials are a little bit quicker. Okay, so now we can go find C. Let's go. Let's go 1 to 5. So now let's go find C. But, and you don't even have to write this, I can just write it. To find C, what do we need? To find C, we need the slope at the endpoints. And to find the slope at the endpoints, we need the y values. We're literally going back to the old method because we're finding the slope of a line of 2 points, not one instantaneous one, but 2 points. So we need the y values. So let's go off to the side and find the y values. So when x is 1, what is y? So technically we're finding f of a, which is f of 1. Okay. So 4 plus the square root of 1 minus 1. And that gives us square root of 0, which is 0. And so that gives us then 4. 4 plus 0. Okay, let's go find f of b, which is f of 5. And remember, don't forget, you're going back to the original. We're talking about this original graph. 4 plus the square root of 5 minus 1. This is the square root of 4, and the square root of 4 is 2. 2. So we can, it's up to you, we can write it as like points. We could write it as 1 comma 4 and then 5 comma 6. Or you can just read it from what you just found, however you like. I like to just go write it like this and then write y2 minus y1 over x2 minus x1. But I just literally do y2 minus y1 over x2 minus x. I think I erased it. Any ideas what we should write here? You just want to go find the derivative. Okay? And that's just up to you if you want to leave it as an x or a c. That's just immaterial. But what did we find? Okay, for the derivative, I think I even circled them just to talk about it. You could write it like this. Was this our derivative? But I think this is the better choice. 1 over 2 square root of x minus 1. Those two are the same thing. And so we'll plug that in over here. So 1 over 2, and then I'll just change it to c. Sometimes I change it, sometimes I don't. Okay, so let's get a fresh board and then let's solve that equation. So let's bring it up here. 1 over 2 square root of c minus 1 equals, and then let's go ahead and change that. That would be 2/4 or 1/2. Are we okay with this? I could write it down here. It's 2/4. So when I go, I might as well change it to 1/2. Then there's a lot of different ways to solve this. I would probably just cross multiply. There's some things, because they're both 2's, there's some other things we could do, but I think just the easiest is to cross multiply. 2 times 1 is 2, and it equals this times 1, so just 2 square root of c minus 1. Okay, so how are we going to solve this? Divide both sides by 2. Beautiful. And then everything else is under the square root, so we want to square both sides. This cancels nicely, so now we just have c minus 1. And then add a 1 to both sides. Okay, was 2 our answer to our last one? Okay, so what does that 2 mean? This is the x value that has the tangent line that has the same slope as the slope of the line that goes through our endpoints. All right, let's try one more. I think this one will go a little quicker. One more. That was probably, like I said, that was even maybe a little bit harder than the one on the homework. This last one matches pretty well. We'll go ahead and basic directions. We'll start all the way at the top. It's just a little bit more room. All right, last one. F of x equals 7 minus 5 over x. And we're going from 1 to 5. Okay. All right, so we want to find point or points. I think all of ours are just one, but there could actually be more than one point that has the same slope as these endpoints, or the slope of the line that goes through the endpoint. But we first have to do a quick check. What do we have to do? We have to check that it's continuous and differentiable. So where is there a problem? Where is this graph not continuous? And again, it's a lot more to write out than just kind of look at it, say it, and know it. But I want us to make sure that we understand, and you got to show me on the test that you at least looked at these. Okay. So where's the problem? This is good. We gotta know where there's a problem. Problem is when x is 0. When x is 0, we get undefined. That's an issue. We can't do undefined. We can't do 7 minus undefined, so it doesn't even matter if there's more. When x is 0, x cannot equal 0. Is that okay? Absolutely, because we're going from 1 to 5. So as long as you say, hey, the problem is just where x can't equal 0, then you can say f of x is continuous on, or you can even just write it something like that. To be honest, even on the test, I would be okay if you just put something like x cannot equal 0. You know, just so that I knew you checked, you understood that 0 is not in this interval. All right, 2 says we got to check the derivative. Do we have any problems between 1 and 5 for the derivative? So for 2, I'm going to first write f of x as 7 minus 5x to the negative 1. As much as we like how they gave it to us, when we're doing derivatives, we need exponents. We need everything on one level, we need exponents. So let's go find the derivative. Derivative of 7 goes away. The derivative here, roll it down. Now we just happen to have a negative 5. Doesn't matter how much space there is. This is still a negative 5. Negative 5 times negative 1 makes it a positive 5. And then don't forget you subtract 1. So that takes us to negative 2. So where would the issue be for the derivative? Actually, the issue would be where x is 0, but we even kind of said, hey, that's not even in the domain. So we really don't have any problems. Okay, the only problem would be at 0, but we actually determined that on the original graph. So yeah, so it is definitely differentiable. It's definitely differentiable on the open interval from 1 to 5. That only issue is 0, and it was 0 back as a problem for the original graph. Okay, so now we can go to this guy. Now we can go to the conclusion that the slope of the endpoints versus the slope at one point. There has to be one point that has the same slope as the slope of the line that goes through the endpoints. So the only other issue is for this problem is we have to find these y's. We were only given the x's. So we have to go find f of a, which is f of 1. 7 minus 5 over 1, that's not too bad. So that's 7 minus 5, which gives us 2. And then we have to go find f of b. We have to go find our y's. B is 5. They give us nice numbers here. They give us, so we plug in a 5. But 5 over 5 is 1. So 7 minus 1 is 1. And so if you just want to take this and plug it in, you can. I just like to write it as a 0.1 comma 2 and 5 comma 6. Okay, and then I can't remember what. I think I'm okay. I thought one time I erased something that you needed. We can leave the original. Oh yeah, I erased the derivative. There we go. All right. So if you haven't written this time you could. I just wanted to reference this paper. Now you would have to officially write it though, or at least understand where it's coming from. Okay, this guy. I just erased it. What was the derivative? The derivative was this, which wasn't too bad, but I would go ahead and write it as 5 over c squared. So I'll go ahead and put in the c. Yes?
Sorry, I missed how you got 5x to the negative 2 as the derivative.
Okay, all right, so let's back that up. So let's let's see, let's write f of x. I'm going to rewrite it this. 7 minus 5, but I'm going to write it as x to the negative 1. Okay. So this, you see how that's just this guy. Okay, so now when we take the derivative of 7 goes away, and then we're just doing 2 terms here separate. So this one, we're just going to roll it down. When we roll it down, negative 5 times negative 1, so that gives us positive 5. And then when we subtract 1, takes us to negative 2. Yeah, no problem. So this is our derivative, or maybe now that we wrote it, this will be a good spot to write it, that we could also write it as push the x down and write it over x squared. And then my only thing, or not my only thing, but I usually write it as x, to be honest, but you know, if we want to identify it specifically as c, then I'll transition from the x to the c. Okay, so now let's do y2. I got my points here, y2 minus y1 over x2 minus x1. Oh, that's not nice. So that's 4 over 4, which is 1. So we can do this as 5 over c squared, and then 4 over 4. I might write this as 1 over 1. Since this is a fraction, I always like to cross multiply. So I would cross multiply 5 times 1 equals c squared times 1. And then how do we undo the square? Take the square root. If you introduce the square root, good news. Okay, so you can just kind of watch this. If you introduce a square root, you're supposed to do plus or minus. But what is wrong, and that means 2 answers. How come this one gets tossed anyways? Do we know why that one's tossed? Because don't forget they give us an interval, right? So a negative would not fall between them. Hopefully the square root of 5 does fall between there. I think. So if you forget about the negative, that's usually okay. Most of the time we are dealing with positives. So most of the time you don't even have to worry about it. Good, okay. All right, let's take a look at this word problem. Because this is kind of cool. It kind of gives us a, you know, we're doing all this math, but what is the purpose of it? And the application, you don't even need an equation, which is kind of cool. So if you're out there, hopefully you have it from yesterday. I can share it, maybe. Oh, I don't know. Actually, hang on. If I want to share, I'm going to share it for 1 minute, and then you guys will have to share. I think this works. Let's go here. Share. So we're going to do this guy. We could read it. We'll just read it here. Oh, do you guys all have it? In the building, out of the building, you have to read it, and then you can either reference it or we'll go back to the board. But 2 stationary patrol cars equipped with radar are located 5 miles apart on a highway. As a truck passes the first patrol car, its speed is 55 miles an hour. 4 minutes later, when the truck passes the second patrol car, its speed is 50 miles per hour. But we can prove that the truck went faster than the speed limit. Prove that the truck must have exceeded the speed limit at some time during the 4 minutes. Okay. And believe it or not, we don't even need the 55 miles an hour and 50 miles an hour. That's just showing you that all that's doing is showing you that when they clocked him, he was going the speed limit. We don't even need that 55 and 50. So let's do a new share. Let's go back to the board. Okay. All right, so let's figure out what's going on here. And I don't know if I'm assuming I got this from a book, but we got to make up a speed limit. Well, let's say the speed limit is 65. So on your paper, you could draw a little box, like a sign, like the corner rounded, speed limit 65. Okay. So can we prove that at some point he went over 65? And like I said, we don't actually even use the 55 miles per hour or 50 miles per hour. Whenever you're graphing, what is always x? X is always time. X is going to be time. X is going to be time. And y is going to be, does anyone want to try to guess? Y is distance. Y is distance. So that makes sense that with these two pieces of information, we'll be able to do miles per hour, and we'll be able to do a rate. All right, so I know at 4 minutes, what's his distance? His distance, not his speed, but his distance. At 4 minutes, what did you say? Yeah, do we see that? It is actually worded. I was like, oh, okay, this is a little bit harder, like to find the word. But yeah, so it starts, and then the whole problem stops after 4 minutes, and how far apart it was at the original sentence was 5. So this point here is 4, 5. Now, what is the time when the problem starts? The problem starts at the beginning of time. That's where the whole problem is. And so how far has he traveled at the beginning? 0. So the first point is 0. So the problem starts at 0, 0. And it ends at 4, 5. And so whatever the slope of that line is, I know that there's a point out there that has the same slope. And the slope of that line is the speed or the rate. So let's go find this speed. y2 minus y1 over x2 minus x1. Okay, so I get 5 over 4 or 1.25. What the heck did we just find? The only problem is this is miles per, not hours. What is it? Miles per minute, because 4 was in minutes. So this is miles per minute. So let's convert that to hours. So 1.25 miles over 1 minute. We want to go to, we want miles per, we want hours on the bottom when we want to get rid of minutes. Or if some of you just know you multiply by 60, if that makes sense to you, that's fine. But this is kind of like officially how you do it. The minutes cancel, units cancel, just like numbers. And now I have miles per. Remember, per just means fraction bar. Miles per hour. Right? That is that 75? So the slope of this line is the 5/4, or converted over to hours, 75 over 1. What does the mean value theorem tell us? If that's the average, there has to be a time when he was going 75 miles an hour. How'd you like that? Officer come and say, you've got a ticket, because I know from the mean value theorem that you were going 75. You could argue, though, what does it have to be, though? It has to be continuous and differentiable. Rip it up and give it back. But chances are you would have stopped, which would have meant you were probably even going faster, right? If it wasn't continuous, it was probably a stop. So it's kind of cool. One way, and that's kind of the neat thing. Like we do all this stuff with equations, but once you go to apply it, you don't even always need the equations. And the other thing, can I tell you where this spot is? No, because I don't have the equation, I can't go find C. So I know C exists because of the mean value theorem says, hey, if this slope has to match at least one of the slopes out there. But I can't tell you where it was. All right, so we're gonna get to the other one, so that's okay. I'll make yesterday's problem 6 extra credit, so don't even worry about that. And then you have 3 tonight. Okay, all 3 tonight deal with the mean value theorem. All right, good job, guys.